Section 5.5 is where we're headed next. We've solved a system graphically. We've solved a system using substitution. We've solved a system using linear combination or elimination. And now we're getting ready to solve a system using matrices. But before we can do that, we have to find out a little more about our matrices. Even though we studied them in last chapter, we have to, as you can see, find out what the determinant is and the inverse of a square matrix. So to do that, before we even solve a system, let's talk about our fourth and final method, solving a system using matrices. But the point is of this lesson is before we can do that, which will actually happen in the next section, we first need to review inverses. So, what is an inverse? From our vocabulary, you should have a good definition. If you said something like, the inverse is like the opposite of something. Well, if you mean opposite is you must flip or switch the x and y values. So in an ordered pair, if I have the ordered pair xy, its inverse, if that's the original ordered pair, then its inverse would be yx. We've also done inverses on equations. Y equals mx plus b, our linear equation, slope-intercept form, whichever you choose. And we said to make this, if that's the original, to make it the inverse, again, we'd switch x and y. And to do that, we'd have x equals my plus b. But then we'd have to solve that for y. So we've done it with lines also. So we would subtract the b. Then we would divide by that m value, whatever it is. And we'd have our final equation, y equals the quantity x minus b, all divided by m. And of course the m and the b are numbers, so that makes sense. It'll be at fractions. But with matrices, it's slightly different. So let's check these bullet points and see if we understand them all first about matrices. So, inverse matrices exist if and only if, when you multiply your two matrices, you get the product 1, 0, 0, 1, which we called the identity matrix. So, I can't even begin to say, oh, can I use any combination of stuff? Well, no, because we're looking at 2 by 2s here. 1, 0, 0, 1 is a 2 by 2. So we're going to stick to using 2 by 2s. All right, second bullet point. Not all matrices represent transformations. So we've been talking about sliding things, reflecting, rotations, using those transformations. But remember, not all 2 by 2s represent a transformation. So, third bullet, not all matrices have inverses. So there's a good important thing to remember. Next one, square matrices have inverses. So when we talk about a square matrices, if you remember our definition, a 2 by 2 was square, a 3 by 3, a 9 by 9. Basically where the length and width or row and column combination in our dimensions have to match. So your number of rows has to match your number of columns. Notation. We used x to the negative first power to mean the inverse of our number x. It will also mean inverse of a matrix. So if I know my matrix is M, M's inverse would be M to the negative first power. Okay, easy enough, some basic stats we need. So let's go to this statement. If I gave you the 2 by 2 matrix 2005, asked you to multiply it by 1/20015, you would definitely get 1001. Remember, when you multiply this, you're doing row by column, and you do second row, first column, second row, second column, okay? And you add up those combinations for 2 by 2 multiplication. if when we multiply two matrices, and again, if we can call them just A and B matrix, and that A and B equals the identity, then we say we have inverses. So this inverse is obvious. So if I have if you look at it carefully, my scale change matrix of 2, 5 in this first matrix, and then the scale change matrix of 1/2, 1/5, those two movements are inverses of each other. But not all matrices are like that, so they all will not be done that way. We're going to use the Matrix Theorem that says we first need to find out what the determinant is. Okay? So it says if AD minus BC, so take a look. Where is AD? AD is the left diagonal. So we're talking about taking these two values on the left diagonal, multiplying them together. Then taking B and C, which are the right diagonal. So the left diagonal's product minus the right diagonal's product. As long as that does not equal 0, then an inverse exists, and we can find it. So this AD minus BC, from here on out, will be called the determinant in a 2 by 2. So notice our size of our matrix right now. We're just dealing with 2 by 2s, and we'll probably stick to that mostly. So left diagonal's product minus the right diagonal's product has to be 0 in order not to be able to get an inverse. If it comes out to anything but 0, we get an inverse. Now look carefully. The work here says that that inverse is right here. So this huge, and huge, it's not huge, remember, it's only a 2 by 2. Here's the first row. Here's the second row. I have a first column and a second column. So we have 4 parts there. Okay, now, in these 4 parts, let's take a look. ADCB was our original matrix. So now I want you to compare that to this one that we're calling the inverse and see if you notice a pattern or see anything, because we didn't put any numbers in. So look hard. And I'm hoping to say that this AD minus BC that we did over here, this determinant, is the bottom denominator on every single one of these. So if you have to do the determinant anyway, it's going to be a piece of your calculation of your inverse. Oh, makes sense. Now look at the numerators. AD was on the left diagonal. What do we have on the left diagonal? Well, we have DA. So it's the same exact thing, but switched around. Oh, that's an easy one. And then look at the right diagonal. It used to be BC. Well, now it's opposite of B, opposite of C. So all they did was switch the signs on the right diagonal. So if I was going to say something and put this inverse representation into words, it might be take your original matrix, the left diagonal's product minus the right diagonal's product gives you your determinant. That is the number you put at the denominator of each of these. Then you look at the left diagonal in your original matrix and switch the positions. D goes to A goes to D. In the right diagonal, you take the numbers that are there and turn them to their opposites. So we'd have the opposite of B, opposite of C. All right, with that, we're going to try a few. So it says, find the inverse of each matrix. And if we have our matrices here, the first thing is you must use that determinant. So remember our determinant, I'll write it up here, AD minus BC. Left diagonal's product minus the right diagonal's product. So you start thinking, all right, left diagonal, 4 times 1 is 4. Negative 3 times 2 is negative 6. The product, 4, or the subtraction of those two products, 4 subtracted negative 6 adds up to 10. 10 is not 0, so we know an inverse exists, and we should be able to write it. So let's do that. Our inverse, if we come over on our 2 by 2, we just said every inverse has its determinant in its denominator. All right, so every element. Now, I didn't give myself a lot of room here, but let's now write the numerator. So look back at your original, and our original 4, 1 on the AD left diagonal. It should now be 1, 4. On the right diagonal, we said just switch the sign. So the negative 3 would become a 3. The 2 would become a negative 2. The last but not least step is to reduce those fractions, write them in a better way, lowest terms. So 1/10, I'm going to write on a diagonal this time, 3/10 in the upper right-hand corner. Lower left would be 1/5, lowest terms, and lower right would be 2/5, lowest terms. So there is our final answer that represents the inverse of our original matrix. Let's follow that along in the next one. Again, same thing. Let's do our determinant. And DET sometimes is also that shortcut for determinant. So DET equals, do the left diagonal. Well, you know that's negative 12. Minus the right diagonal. That's also a negative 12. But a negative 12 minus a negative 12 gives us a total of 0. If it gives us a total of 0, we have no inverse that we can write. Okay, good enough. Let's go to the last one. What is our determinant? You always have to figure the determinant to determine whether an inverse exists. That's the whole key. So the determinant, left diagonal's product, 11 times 2 is 22, minus the right diagonal's product, 3 times 7 is 21. 22 take away 21 is a 1. So our determinant is not 0. It means an inverse exists, and it means we should be able to write it. So again, set up a shell, an empty shell of our 2 by 2. And again, we said every piece, every element has its determinant in the denominator. Well, this makes it easy. Our determinant is a 1. So we're really going to get whole numbers on this one. Absolutely. Now let's follow the rule. Left diagonal, you switch the numbers positions. So the 2 goes to where the 11 was, the 11 goes to where the 2 was. On the right diagonal, we switch to their opposites. So we get a negative 3 where the 3 was at, we get a negative 7 where the 7 was at. Last but not least, simplify. Easiest possible would be the whole numbers. So this matrix, this 2 by 2 matrix, is now the inverse matrix of what we started with. If you would multiply the original matrix times the inverse matrix, what did we say we were going to get? Good. We would get the identity. So if you need to check, you could always do that once you have your inverse. So here's the original. Here's the inverse that we just calculated. Multiplying those two together should give you the identity matrix. All right, you have enough knowledge to get started on some problems for us. We'll come back and work on truly how you solve a system using matrices in the next section. So today it's more or less about how you find inverses. Do they really exist? So use your formula, use your theorem, and you should be good to go.